Hey guys, welcome back to this video. Now we are going to discuss the binary search approach to find median of two sorted arrays. Before diving into this approach, I highly recommend you to watch the part 1 of this video where we solve this problem using two pointers. If you have already watched that part, let's continue. So here we are given two sorted arrays, array A and array B. So when we are going to merge these two arrays, the values which are going to decide the median of the merged sorted arrays are going to be at index 5 and index 6, and those two values are going to be 6 and 7. So we have to find these two values. In our previous approach, we were able to find these two values using two pointers. Now we are going to use binary search in order to find the value at index k in the merged sorted array. We are going to use 2D binary search. So what this means is we are going to use binary search on both the arrays A and B. So in array A, I created two pointers, A start and A end, and the indexes are 0 and 6. And then I find the middle of this array, and let's call it A index, and it can be calculated using A start plus A end divided by 2. And similarly for array B, we have B start, B end and B index. When we are using this formula to find the middle index, this can also lead to an overflow. So keep that in mind. So I'm just simply using this formula, as the test cases do not lead to any overflow issue. So just keep that in mind when using binary search and when we are finding the middle index. So this formula to find the middle index, this is basically going to give us the floor index value. If we instead use a +1 and divide by 2 operation, so this is going to give us a ceiling value index. So we can either use a floor value or a ceiling value. Floor value is highly common in binary search algorithm. So let's stick to it. Let's start by finding the element which is going to be at index 6. So let's say k is equal to 6. Now what we are going to do is we are going to calculate the sum of A index plus B index, and currently this is 3 and this is 2. So this value is equal to 5, and this overall value is currently less than k. So what this means is we are going to find the element at k index towards the right hand side of the merged sorted array. So we need to eliminate the left side of one of the two arrays. Now we have to decide now which left side we have to eliminate, whether we should eliminate the left side of array A or left side of array B. So here we can see that the value at A index is greater than the value at B index, and our final merged sorted array is going to be sorted in ascending order. So we should eliminate the left side from the array which has the smaller value. So we are going to eliminate left side of array B, and we are going to update the value of B start equal to B index plus 1, and this is going to be equal to 3. Now we have incremented B start equal to 3 and we have eliminated these three elements. What this elimination means is that these three elements are going to be present to the left of the value at index k. Now let's move forward. So we calculate B index, and this is going to be B start plus B end divided by 2, which is equal to 3, and our A index and A start and A end are unchanged. Now we check the value of A index plus B index, and this is equal to 6. So this is greater than equal to k. Now we should get rid of the right side of one of the arrays. The array which has a higher value, that array's right side will get eliminated. So array B has a higher value than array A at A index and B index. So we are going to decrement the value of B end, and we are going to set it equal to B index minus 1, and this is going to be equal to 2. And now in this case our B start has become greater than B end, and this is going to be one of the edge case where we can decide the value of the element at index k. So B end is going to come here and B start will be at index 3. This means that in the final merged array, 3 elements from array B are going to be present to the left of the value at index k. So we have these 3 elements from array B, and now we have to decide the value at index 6. Now what is going to happen is these 4 elements are going to come from array A. So we have to find this element from array A. So from array A, the element which is going to be at index 6, that is simply going to be k minus B start, and this is going to be A3, that is element at index 3 in array A, which is value 7. So the element at index 6 in the final merged array is going to be value 7. So what this means is that till index k, 3 elements are going to come from array B and rest of the elements are going to come from array A. And similarly, we can have a situation where A start can become greater than A end, and that would mean that we have finished processing the elements from array A and rest of the elements are going to be picked from array B, and this way we are going to find the element which is going to be at index k using binary search. So the overall time complexity of this approach is going to be O of log m plus log n, or O of log m times n, and space complexity is simply going to be O of 1. So I hope this made sense, and the next question we can ask ourselves is, can we do better than this? So the answer is yes, we can do better, and let's see how we can improve our time complexity. In our optimal approach, we are going to do binary search on the smaller array. We can also do binary search on the bigger array. For that case, our indexes will go out of bounds and we'll have to deal with those cases separately. So first, let's stick to doing binary search on the smaller array, and in the coding implementation, I will cover both the approaches. So I have created the binary search pointers left and right, and we have this array of size 3 and another array of size 6, and currently left pointer is at 0 and right pointer is at 3, and we find the middle using the formula L plus R by 2, and currently this is equal to 1. This variable PA is the partition in our smaller array, and we find the corresponding partition in the bigger array using this formula. So this is going to give us 5 minus 1 equal to 4. So PB is going to be equal to 4. What these partitions mean is, if we select these elements, so we have 4 elements here and 5 elements here. This is our left half in the final merged array, and this is the right half in our final merged array. So we are checking if this is a valid partition such that this is the left half and this is the right half. Now let's see how we can check if this is a valid partition. Currently we have this scenario where PA is at 1 in the first array and PB is equal to 4 in the second array, and in order to check if this partition is valid, we have to compare these 4 variables such that min right A has to be greater than equal to max left B, and min right B has to be greater than equal to max left A, because min right A and min right B are in the right half and max left A and max left B are in the left half of the merged sorted array if this is a valid partition. So we check if 2 is less than equal to 10, so this is correct, but 8 is not less than equal to 4, so that means that this is not a valid partition and we have to consider some other partition so that we can reach a situation where we can calculate the median of the merged sorted array. So in this case, 2 is less than equal to 10, so that means that the left side of array A is correct. So we can move towards the right side of array A and we can update our left pointer equal to PA plus 1. Now we have a situation where our left pointer is at index 2, our right is equal to 3, so we calculate PA and it will come equal to 2, and our PB will be equal to 3. So as you can see, as PA is moving towards the right, our PB will shift towards the left in the bigger array. So now again we compare these 4 values. So we check 4 is less than equal to 8, that is correct, but 7 is not less than equal to 6, so that is incorrect. Now again, this is not a valid partition, so we again going to push our left pointer towards the right. Now we have the situation where our left pointer is incremented to 3, our right is also equal to 3, and our PA will come equal to 3 and PB is going to be equal to 2. Now again we have to compare these 4 values, so we compare max left A with min right B. So 6 is less than equal to 7 and that is correct, and now our max left B is 3, but PA is out of bounds here, so we can use integer.max value when PA gets out of bounds. So when PA becomes equal to M, we can use integer.max value for min right A, and if PA would have become equal to 0, then for max left A we will have to use integer.min value. So 3 is less than equal to max value. So this is also correct. So now this is a valid partition, and our right partition has these 4 elements and our left partition has these 5 elements. And now we can make a decision about the median of the merged sorted array. To make that decision, we have to check if m plus n is odd or even. So in this case, our m plus n is odd. So our median is going to be max of max left A and max left B, and this is equal to max of 6 comma 3, and this is equal to 6. So a median is going to be 6 in merged sorted array. And if m plus n would have been even, then for that case, for the first value, we'll take max of max left A and max left B, and we'll take minimum of min right B and min right A and take their average. So I hope this made sense. Now let's have a look at the coding implementation for binary search approach. To deeply understand the optimal solution where we do binary search on the smaller array and use partition technique, I highly recommend you to watch this coding implementation and do not skip this. Before jumping into that, let's quickly have a look at the 2D binary search approach where we are using binary search on both the arrays. So this is going to be the code of that approach. So as discussed, this is the index k for the final merged array, and we want to find the element at this index k. If final merged array is going to be odd, we know that median is only going to be one value and it is going to be at index n by 2. And if final merged array is of even length, then we have to find two values and take their average, and we have to find the values at index n by 2 and n by 2 minus 1. And initially we are starting with the respective binary search pointers in both the arrays, and we initialize them to 0 and length minus 1, and we have our while loop. And in this while loop, we know that the base case is going to be when a end is going to be less than a start, or b end is going to be less than b start, and we find the middle index and the value at that index. And if the sum of the index is less than k, then we find the smaller value and eliminate that array. And if it is greater than equal to k, then we eliminate the array which has the larger value. And in the inner if else blocks, the equality can either be on if here or it can be in else. So either way it works. But for the outer if else, the equality is going to be in the else block. So here we are using an infinite loop. Instead of an infinite loop, what we could do is we could bring these if blocks outside of the while loop here, and our condition is going to be a end is greater than equal to a start and b end is greater than equal to b start. And I can remove this one, and now if I try to run it, so yeah, that works. Either we can use an infinite loop or we could use these checks. Either is fine. Even though we have an infinite loop here, either of these two if blocks are guaranteed to run. So whenever this code is finished, we are going to be left with either of these two conditions, and we are going to return the value at index k. Now I'm going to cover the optimal approach in detail where we do binary search on smaller array, and we basically partition the array into two halves. So let's have a look at that. The key to understanding the optimal solution is understanding that the number of elements from the first array in left half plus number of elements from the second array in the left half is equal to the half size in the final merged array. So what this means is that we have to decide whether the left half is going to be bigger than the right half or it is going to be smaller than the right half for the case when the total number of elements are odd in the final merged array. And when I say that the number of elements in left half are greater than the number of elements in right half, it means that the left half just has one more extra element than the right half, or the left half has one less element than the right half for the odd case, and for the even case the number of elements must be equal in left half and right half. So when we are creating partition A and partition B, in both the arrays, we can either assume that both the elements are going to be in the right half of the merge sorted array, or we can assume that both the elements can be in the left half of the final merge sorted array, or it can be the case when partition A element is in the right half and partition B is in the left half, or partition A is in the left half or partition B is in the right half. So we have to mathematically decide first which approach we are going to take. In our algorithm walkthrough, we have taken both the partition A and partition B index elements in the right half of the merge sorted array. And if that is the case, then two things can happen. That the right half is going to be bigger than the left half in the merged array, or left half is going to be bigger than the right half in the merged array. Let's say if the right half is bigger than the left half, then we can use either of these two formulas to find partition A or partition B. And if left half is going to be bigger than the right half, then we can use either of these two formulas. In our algorithm walkthrough, we discussed this approach where the left half is going to be bigger than the right half. So let's try to understand this. Initially we set left equal to 0 and right equal to m. So initially we have set right equal to m and not m minus 1. So what this means is that when we are going to make a cut on the first array, that is the partition A index, then that partition A index element is not included in the left half. So whatever elements we have before partition A index, those elements are going to be in the left half, and starting from partition A index, those elements are going to be in the right half. And similarly, based on that idea, we know that the element at partition B index is going to be in the right half of the merge sorted array. Keeping that in mind, mathematically we are going to come up with this value to decide the value of partition B, and we subtract partition A from this value to get partition B. And initially, let's say if partition A is 0, then that means that the left half is empty and right half has all the elements. And if partition A becomes equal to m, then left half has all the elements from the first array and the right half has no element. And we know for this case that the left half is going to be bigger than the right half. So for the case when the final merge sorted array is odd, then the median is going to be the maximum value of max left A and max left B. And for the case when the total length is even, then we have to take the average of max value of these two values and minimum of these two values. And these are the four values that are compared to find if a partition is valid or not. And we know that if partition A becomes 0, then the left half is empty, and it means that the max left A value will be min value, and if it becomes equal to m, then it's simply going to be max value. And similarly for the second array. And these two else blocks are to move our binary search pointers. Now what happens if our right half is bigger in the merge sorted array? For that, our mathematical values will change. Instead of +1, we'll just have m plus n divided by 2. So this is basically going to shift the value of partition B towards the left. And since the value at index partition B is in the right half, so this is going to make the right half bigger in the final merged array. Now instead of taking the max of max left A and max left B, we have to take min of min right A and min right B. So now our right half is bigger. So let's try to run this one. So that got accepted, which is great. And also test the previous case as well. And we have to also update our mathematical value. So let's try to run it. So that works, which is great. And we can also use different values as well. So for the case when right half is bigger than the left half, we can either use left plus right by 2 or left plus right plus 1 divided by 2 to find the partition A. And what's going to happen is if we use this value, then for the first array, right half is going to be bigger for the first array only if it is odd. And if we use a +1, left half for the first array is going to be bigger if the first array is odd. But overall, This value is going to make the right half bigger in the final merged array, regardless of whether the left half in the first array is bigger or not. The second value compensates for that and makes the right half bigger. The key to understanding this binary search approach is to understand these four cases when partition A and partition B are in the right half of the merge sorted array. We can also take partition A and partition B in the left half of the merge sorted array. Now what is going to happen? If we take the elements at index partition A and partition B in the left half of the merge sorted array, then what is going to be the number of elements in the left half from the first array? It is going to be equal to partition A plus 1, because this index partition A is 0 based. So partition plus 1 is going to give me the elements from nums1 in left half. For the previous case, the number of elements from nums1 in left half was equal to partition A, because partition A index element was not in the left half itself, and since it is 0 based indexing, the number of elements was partition A itself, and now partition A element is in the left half, so the number of elements is going to be equal to partition A plus 1. And for our elements from the second array, it is going to be equal to partition B plus 1. And this value is going to be decided based on whether we take left half to be bigger or right half to be bigger. Let's take the left half to be bigger, and we can set this equal to m plus n plus 1 divided by 2, and our partition A plus partition B is going to be equal to m plus n plus 1 divided by 2 minus 2. So in our code now, we are finding our partition B using this and partition A using the original value. And here you can see that we have updated our left and right equal to -1 and m minus 1. This is because now we are taking the elements at partition A and partition B indexes in the left half. So the cuts that we are making in both the arrays, we are including the element at that particular cut. So if we make a cut at m minus 1, now that element is included. For the previous case, we had to make a cut at m to include the element at m minus 1. And similarly, when we are making a cut at -1, it means that the left half is empty. And for our previous case, we were setting it to 0 because we were not including the element at index 0 and our left half was empty. I hope this is now making a better sense about how this algorithm is working and how we are coming up with our coding solution. And moving on, again we have these four values, and our base cases are going to be these four conditions. When partition A becomes equal to -1, it becomes equal to m minus 1, and similarly -1 and n minus 1 for partition B. And now since partition A is in the left half, so we have to take the element at index partition A plus 1 in our right half, and we set min right A equal to that index value when it is not equal to m minus 1, and similarly for max left B and min right B. And now going on, this is for the case when overall array is odd and our left half is bigger, and we take the average of the two values again, and these are again for moving our binary search pointers. And now we can also come up with more mathematical values. It is not necessary to just use these values. The whole algorithm is governed by this sum. So based on this sum, we come up with this mathematical formula and setting of these pointers. If you are able to understand how this sum is working, then writing this code really becomes a piece of cake. So I highly recommend you to draw diagrams and do a detailed walkthrough for all the cases when the partition A index value and partition B index value are in the right half and when they are in the left half. And now what if the element at partition A index is in the right half and value at index partition B is in the left half? Now what's going to happen? Now if element at partition A index is in right half and element at index partition B is in left half of merge sorted array, then the number of elements from nums1 is going to be equal to partition A, and from the second array it's going to be equal to partition B plus 1. So the value of our partition B is going to be equal to m plus n plus 1 divided by 2 minus partition A minus 1, and again we have taken the left half to be greater than the right half in the final sorted array. So our base cases are kind of interesting now. For the partition A, we are comparing it with 0 and m, and for partition B we are taking minus 1 and n minus 1 for the base cases, and initially we have assigned left and right equal to 0 and m. This is because partition A is in the right half, so basically the cut at that index does not include that element in the left half, so that is why we have to go all the way till m instead of m minus 1. And for our partition B, that index includes that element in the left half, so we can go from minus 1 till n minus 1. And when this is not the case, we have to take the element at index partition A minus 1 for the first array, for max left A, and for min right A we have to take the element at index partition A. And now for our second array, we are taking the element at partition B as max left B, and element at index partition B plus 1 for min right B. And our binary search logic mostly remains unchanged. Only this else will change depending on whether the right half is bigger than the left half or left half is bigger. So I hope this made sense. And again, to understand this deeply, I highly recommend you to draw diagrams. So the test case that you can use to understand this algorithm is to take one array of even length and another array of odd length, so that the sum of the lengths is odd, so that you can understand this odd case, because for the odd case only our median changes. So I highly recommend you to do that. So this was the algorithm when we are doing the binary search on the smaller array. Now what if we want to do binary search on the bigger array instead of smaller array? So we're going to use a similar logic where we have our both the partitions. The only thing that is going to change is that when we are finding the second cut or the second partition, it could happen that the value of partition B or value of cut 2 here in this code, it can be less than 0 or it can be greater than the value of the length of the second array. And if it gets less than 0, then it means that we have taken too many elements from the bigger array. So we simply decrement our high pointer and set it to cut 1 minus 1. And if it becomes greater than n2, then it means that we have not taken enough elements from the bigger array. So we set our low equal to cut 1 plus 1, and rest of the logic remains same. The only thing we have to be careful is that the value of second partition can go out of bounds, because it is the smaller array now, and when we were doing binary search on the smaller array, the value of second partition or cut 2 was within the bounds, so we did not have to worry about this. So this is the code for our binary search on the bigger array. So let's try to run this. So this one works, which is nice. So I hope this made sense. This approach can be confusing, but to master this approach or to master binary search, it is all about understanding the odd length case, that either of the two arrays can be bigger, and at the same time we have to be sure that for the even case that the number of elements are equal, and as long as the number of elements are equal for the even case, we can have either of the halves bigger for the odd case. In this coding implementation, I have not taken the overflow into account because the test cases work without taking that into account. But for binary search solution, we should find our middle index using this. So for this coding solution, I have taken the overflow into account, and instead of using low plus high divided by 2, I use this so that we do not overflow. So keep that in mind. The main purpose was to explain the partition logic anyway. So I hope this made sense. If you have any doubts, let me know in the comments. And I highly encourage you to spend few days on this problem. Then only you're going to master it. So thank you so much for watching, and I'll see you in the next one.